Alright, so today's training will take you from getting a protein crystal structure all the way through to preparing it for any number of operations to do within Maestro. That could include docking or water mapping or FEP+, but this is how you're going to prepare any protein for any number of tasks. So here is the source of all knowledge, RCSB. This is where all crystal structures and NMR structures of proteins are kept. And we're interested in a protein called DJ1, and it causes Parkinson. And I'm going to put in Homo there, short for Homo sapiens, to narrow it down. And then for the stuff we do, we always want to have the best resolution possible, and we want to take a trusted crystallographer as well. So this is DJ1 best resolution, but this A104T, if we did some reading, we'd find out that's a mutation that actually causes Parkinson. Whereas this is human DJ1 wild type, and it is 1PF5. 1.1 angstroms, that is very good. So we found our 1PF5, and that is the first part of this exercise. Now in the second part of this exercise, what you're going to want to do is go to the tutorials from within Maestro. This is Schrodinger's program. You will need to access that from on campus because we have a site-wide license, and go to 22 Introduction to Structure Preparation, or you'll find this anywhere else. You just need to search Protein Preparation Wizard, and what I'm going to describe, you're going to go through this step by step and do. Alright, so if we were to do that, the first thing we do is we've already found our protein, which you'll remember is 1PF5. We'll download that. This is the human protein DJ1. So that was the first step, get PDF. Second is to open this protein preparation wizard. Okay, could have just clicked prepare, in fact. And we are waiting. After clicking the protein preparation wizard here, this will open. And then the first thing we're going to do is on this important process tab, we are going to switch to a faster processor here, just because I can. Have another computer sitting over there. We're not going to align this because it's the first structure we brought in from DJ1. It's going to be alone. There's no reason to align it to another structure in here. As we bring in further structures, we can align them to this structure. It makes them easier to look at because they look similar. I would say use the defaults. Don't worry about it. Although I like to do this. If there's anything missing, we can fill them in with some advanced molecular modeling tools. I am not going to delete waters because I want to do some water mapping, which I'm going to train you to do as well. So here we are, and then we would just click pre-process. That would be now stage 1 of our protein preparation. Okay, this pops up when the calculations are complete. We do have a couple of overlapping atoms. I'm not going to worry about that right now because we're going to take care of that most likely in the minimization process of this, which is the third part. So for now, I'm going to close these. We're going to come back to this though, don't worry. Now we can go on to the next. Again, we're not going to do that yet until we've refined the structure a little bit. Now we're going to sample water orientations because in the crystal structures they have no idea which way. They can't see the hydrogen, so they don't know which way the waters are. We are going to keep the defaults here and just click optimize. That's part 2. Alright, so you'll see here that this optimized hydrogen bond job is incorporated, and if we couldn't be sure, we would have seen here that we had our original structure, our pre-process, which was done on this first tab, hydrogen bond here, and now we want to do a restrained minimization using default parameters, including default force field, and click minimize. And that will end the process of our protein preparation, except for going through reviewing and modifying. Okay, our minimization job has been incorporated. That's great. Now I'd like to go back and modify, see what we have wrong here, if anything. And so I'm going to analyze this workspace. We're going to view problems. There are no problems. So the problems that it showed earlier are cleared up. Okay, and sometimes we could These are all of our waters, so it looks like we're good to go. Now next, you will not have access to this next thing, but I wanted to show you why I was preparing them. You're going to go into the glide tutorial, and we're going to see how well you do yourself. Glide docking. You're going to try and dock in small molecules, so you'll build a couple and dock them in. And if you get that right, I'll be oh so impressed. But what I'm going to do with this at this point is something called water mapping, which I'll explain in more detail. But if we go here, water map, and perform calculations, except I'd like to see the water map window. Which is right here. So what I want to do is select the part of the protein that I do a water map on. I'm going to go by chain. I want to actually look at everything. I'm going to add everything. Say OK. Now I'm going to go back to the water map, which just gets hidden over here. Residues. I don't want to truncate the protein. And I want to analyze the whole damn thing. And I'm not going to get rid of the existing waters because somebody went to the trouble of solving them. And then I'm going to run this. And now you've been through one of the most advanced stages of drug development, because depending on the energies of these waters, it tells us how likely we are to be able to put a drug in there. If you have a water that's holding on tightly, it's hard to move out. So you don't want your drugs to fight with water that's tightly bound. So that's what this next generation stuff does.